Okay, time to get started. So let's see. Last time, well, we weren't quite there yet, were we? Okay, so here's what we had been talking about. We'd been talking about how to parameterize surfaces, and then what can we say about little pieces of the parameterizing space versus little pieces of the surface that it's being used to parameterize. And what we found was various relationships, right, that we can write down based on looking at the coordinate curves and interpreting them as velocities, et cetera, et cetera. I'm not going to repeat all of that. Okay, so there's a special case I want to point out, and that is if you are using a graph parameterization. Right? So specifically, remember that the graph parameterization is this thing right here, and I'm going to take the case where the input parameters are x and y. Not that it really matters, as an analogous version of this when you have the other variables playing different orders. But here's the thing: if you are using this graph parameterization, then your xs and your xt are always that formula, right? So why recompute that every single time, right? We're going to be using a lot of graph parameterizations, and it's kind of nice to have that already done. And then likewise, this is going to be the cross product every single time. And this is going to be its magnitude every single time. So I think it's a good idea to have this formula memorized also. Now, you don't have to, right? You can go through this calculation every time. It's not that bad, right? But because graph parameterization is, again, so common, right, it saves you a couple of steps, and it is kind of nice. Now, I do emphasize, though, this formula right here is no substitute for the general formula. Namely, general formula is to know what capital N is and to know how it's computed from these partials of the parameterization, etc. That works for every parameterization. This formula right here is only, I emphasize, only valid for the graph parameterization, which is a sometimes thing. It's not an always thing, right? So this is a supplemental. It is not an alternative. Does that make sense to everybody, I hope? Okay. All right. So, okay. Well, now I'm going to point out that if you take a close look at that little bit of the formula, you'll notice that that is exactly the square of the magnitude of the gradient. And then if you think about it, well, wait a minute. The magnitude of the gradient is the steepness of the graph. And so you get this nice little formula too, and this is, I don't think this is something you should memorize particularly, but I think it's a nice observation to make, and it allows in some cases for some shockingly convenient computations. And I wanted to show you one of these. This has come up in real life for me, and so I think it's entertaining, you know, when those instances when multivariable calculus show up in real life. It's kind of nice, right? Yeah, suppose this is your house, let's just say. A very crude drawing, right? But you get the approximate idea. You see the walls, and the foundation footprint, and then you see the roof up there. And I hope this shape of roof is kind of recognizable, this kind of thing. Now, of course, you know, architects are creative people, and there's all sorts of different kinds of shapes of roofs. But what is actually really common is when you make a roof to have the steepness of the roof be basically constant. Right? And so what you end up with is a bunch of faces that look like what we have here. And if you were to want to compute the area of that, now why in the world would we want to ever compute the area of a roof, right? When's that going to come up? Well, someday, if you ever own a home, you're going to have to pay to have someone put new shingles on your roof, and you're going to be shocked how expensive that is, right? So it's a ton of money, and if you're talking about spending $10,000 or $15,000 on shingles and roofing, right? You don't want to get overcharged. So if they come to you and say, yeah, your roof is this many square feet, wouldn't you like to be able to check that, right? Because that'd be a pretty easy place for them to hide an accident, right? So how would you compute that area? Well, look, it's a triangle plus a parallelogram plus another parallelogram, and you could just go through and do each face like so. The problem is there's next to no right angles, and this is a difficult calculation, right? First of all, there's a bunch of faces, but also they're just not right triangles, and that's a harder calculation than it looks to be. Right? So much easier is to make the realization that what you have up here is a graph. A roof is a graph, and I believe almost all cases, there may be some counterexamples out there, but they're practically all graphs. And to compute the area of a graph, right? Remember, our area stretching factor is that. And wait a second, if we're talking about a roof where the steepness is constant, that means that the whole integrand is a constant. That means that this whole integrand will just factor right on out, leaving you thus only with, leaving you only with the sum of the areas in the footprint. In other words, just the area of the footprint. And the area of the footprint, much easier to measure. You need a tape measure and a 4-function calculator. 2-function calculator, right? You just need to be able to add and multiply, that's it. So really easy calculation to compute the footprint area, and so if you only know that one value, namely the steepness, then your calculation just got a lot easier. So I think it's a neat observation, and I've seen this done in real life, not when I was a homeowner, but when I was my parents were the homeowners, and this is a good way to double check. All right, everybody good with that? Okay. All right, nice little example. Okay, so now we're going to move on to talking about surface integrals. And there's several things to say about surface integrals, and I'm going to go through and talk about all this stuff. But what I want you to be thinking, the through line that I want you all to be thinking about the whole time, let me get over to here, is how much this surface integral conversation that we're about to have, how reminiscent that is of the line integral conversation that we've already had, right? And I deliberately wrote these notes over here to kind of follow the same pattern, to kind of lay out on the page to a reasonable extent. I mean, I didn't bend it over backwards, but I want it to be as reminiscent as possible. So notice, and I'm going to be flipping back and forth throughout the lecture today to say, hey, look, check it out. This is morally equivalent to what we did with integrals on curves, and except that now we're just doing it on surfaces. Okay, so anyway, that's going to be the through line. So what did we do when we asked the question, how would I add things up over a curve? First of all, what do I mean by an integral on a curve? And I mean the same thing that we've always meant on, with the expression integral on any sort of a domain. Whatever the domain is I've got some question that doesn't quite make sense, but if I chop up this domain into little pieces, on each little piece the question makes sense and is easy. Right? So it's the whole is the sum of the parts, chop it up, add it up, however you want to say it, is the big idea. So that motivated this formula for a Riemann sum on a curve, and this notation and this terminology. Well, we're going to do the same thing over here. What should it mean to do an integral on a surface? Okay, well, maybe there's a distribution of mass on that surface, bent surface, whatever. Maybe there's a bunch of ants crawling around on that surface with varying sort of, there's more ants per unit area near the bottom and less ants per unit area near the top, something like that, right? Whatever. And, well, chop it up, add it up, would look like this. This just says, if we look at each little piece, some little piece there, right, on that little piece, quantity per unit area times area gives me quantity. Right? It's just like over here saying that on each little, each little piece, this little piece right here, quantity per unit length times length gives me quantity. Right? Totally analogous idea. It's the same concept applied to a different context. Okay, how are we doing? Does everybody buy that? All right. So, well, we look at this expression right here and declare that a Riemann sum. After all, it looks just like a regular Riemann sum. And this notation comes out pretty naturally for all the same reasons. This is notation, integral notation to represent a little piece of area. So ds, natural thing to call it. This notation right here is a representation of a 2-index Riemann sum. So, yeah, double integral notation seems to make sense, right? And of course, you got to say what your domain is, and as usual, we'll make that a subscript, as we've done with every other integral we've defined. So this notation makes sense. And in the same way that we call this not just a line integral, it's integral over a, loosely speaking, over a line, right? Forgive the sloppiness of the language. We furthermore call this a scalar line integral because all of the participants are scalars. Well, likewise over here, we're going to call this a surface integral because it's an integral over a surface, and scalar surface integral because little piece of area is a scalar. This integrand density type thing is a scalar. So, and again, why do we feel the need to have this qualification in here at all? Well, it's because there's another one coming. And you can probably guess. It's going to be, I'm going to go ahead and give it away because this is obvious. It's going to be called a vector surface integral, right? But we're not ready to talk about that just yet. We'll get to that very soon, later today. Okay, so what did we do with line integrals? We observed that parametrizations are a way to view my dimensionally awkward curve domain as an image. And when you have an image, you can play pullback and stretching factor games and calculations and details. Oh, okay. Same game here. Right? So, again, a parametrization of a surface allows me to view the surface as an image. And when you have a domain viewed as an image, then you can pull back and play stretching factor games. And in fact, we've already played those games, right? That was the calculations that we did last time. Everything that we need here is actually already looking at us here. So I need to know what is this little piece of area here, that little piece of area ds, and how does that relate to this little piece of area over here, ds dt, and well, okay, we already did that work. We've already found, kind of, one could even say inadvertently, that this is my relationship between input area and output area. It's the magnitude of capital N, being computed by that formula. Already figured it out. So that's our stretching factor. That's what we put in here when we pull back through the parametrization. That's what we put in here when we want to make the differentials ds dt, right? To sort of make it right, as it were. Right? That's what makes it legal. So again, hopefully this is all very familiar. At least, structurally, by analogy. And of course, this is brand new in terms of the details. How are we doing? Is everybody on board so far? Okay. All right. So, before we get into a calculation, let's ask the reasonable concern. This formula here does seem to depend on the parametrization, but on the other hand, this expression over here should be intrinsic to the surface, and I don't think it ought to depend on the parametrization. So, is this actually independent of the parametrization? And yep, it is. So it's good to be concerned about this. And if this were a extremely mathy, proofy multi-class like Math 222 or something, then I would go through and worry about that, and we'd prove that this is independent of the parameterization. This is not that course. So I'm just going to note that it's a good concern, and that the answer is yes, and everything's fine. There's nothing to worry about, and we're going to skip right over this business. Okay, so you'll see a lot of stuff in the book, by the way, a lot of discussions of, why is this. And y'all don't need to worry about that at all. Okay. All right, so let's see an example. By the way, doesn't this look familiar? And let's see, let me go ahead and do this and come down here. And you remember we did something structurally very similar. I gave you some parameters for a particular curve with mass distributed by a certain density, and I wanted to compute various different things. And we did 4 kind of simultaneous integrals because, after all, same curve, same parameterization, same velocity, same stretching factor, same density. A lot of the stuff was the same in all 4 of these integrals, right? So likewise, we're going to do the same thing now over here. So let's suppose I have mass distributed across the upper unit hemisphere, right? And for whatever reason, density is given by height. So the higher you go on this hemisphere, the more mass there is. And with that distribution of mass, let's ask, well, what is the total mass? Where is the center of mass? And what is the moment of inertia around, let's say, the z-axis? Not that it matters much in terms of how to do it. And what did we do over here with the curve? Well, we followed the formula and found the stretching factor. So same thing over here. Given a parameterization, now this is the upper unit hemisphere. Spherical coordinates is awfully convenient when you're parameterizing something on a sphere, right? Some subset of the sphere. And so you end up with this parameterization we've seen several times previously. Make sure you're good with that. Make sure you remember and that you can get to that sort of thing yourself. And plug and chug. And we've already done that as well. Well, we've done most of it. I left some of that algebra as exercises for y'all last time. Okay, so we've got ourselves a stretching factor, and we're in business. So I'm only going to go through one of these calculations because they're all morally the same. I mean, yes, of course, they're a little different. I mean, the formula for moment of inertia is different from the formula for mass. Of course it is. Yeah, reasonable, right? But the how to compute a scalar surface integral aspect of it, it's all the same, right? So let me focus on just this one calculation here. Chop it up, add it up, says that mass is double integral dm. You'll notice I'm using integral shorthand here. Mass is density times size. Now, you got to think about the context here. The mass is distributed over a surface. We are adding up over a surface. Little piece of area of a surface is ds. Is everybody happy with that? Okay. Right, okay, well, ds is stretching factor times your parameter differential, so in this case, d phi d theta, right, from the previous page. And so a few things to plug in. So on the one hand, here's my stretching factor that I've already computed. That was sine phi, so we stick that in there, like so. Right? Just plugging in. Don't forget that the density was given. The density was given that as z, so density is z. That's another plug-in, just a matter of doing it. And then the one last thing I'm going to point out, well, I guess I'll say 2 last things. But anyway, so there is the question of what to do with this z thing. What do I do with z? How do I know what z is? Remember, the actual plugging in that you're doing is literally the parameterization. That's what the parameterization gives you, is output variables as functions of the input variables. So in fact, this is z right there. It is cosine phi. Everybody okay with that? All familiar, perhaps, I hope? I think it's a healthy exercise, by the way, to go through the calculations we have over here on the left and the calculations we've just done on the right, and note the strength of the analogy. This is extremely strong, and this is very useful. This will help take all of what you already understand about scalar line integrals and allow you to use that to help you understand correspondingly with scalar surface integrals. Basically the same idea. Alrighty. So let's see here. Moving along. Okay. Excuse me. So, we were looking at line integrals. We came across a certain application that involved a dot product. That was an eyebrow raiser. It seems sort of vector relevant, and so we had to worry about orientations. And the formula for the differential ended up being different, right? Notice this is a dot product. The participants are vectors. It's just a different thing. In some cases, depending on your application, thus giving rise to this new idea of a vector line integral. Right. Work happened to be the application that where we first encountered this. Right? Starting with our sort of simple version of work, our sort of, let's assume that the vector field is constant. Let's assume that the path is a straight line, etc. Okay. All right. Well, here we are with surface integrals. Very, very similar thing is going to happen. The physical concept in question is flux. So y'all may remember this from Chapter 3. We talked about flux. It came up again in Chapter 6 at some point, right? Sort of flux through a curve, analogous idea. But here we are back to surface flux, so three-dimensional flux. And it's computed with a dot product. Now, quick reminder, and this is mostly a Chapter 3 thing, so I'm going to let y'all remind yourself of these details by flipping back into Chapter 3. But the reason that we care about this thing, flux, is for a couple of reasons. And it depends on what your vector field represents. If your vector field represents velocity, then flux gives you volume per unit time of fluid that's flowing through your surface. And that's, a physically natural thing. It's sort of clearly an object of interest, and so flux is a good thing to know, right? But furthermore, don't forget as well, sometimes it makes more sense to represent the fluid flow with density times velocity. And in that case, you'll recall I left as an exercise for y'all to fill in. I repeat, that's a good exercise. Then flux, same formula, F dot N times A, gives you a different natural, interesting, of course you'd be interested, quantity, namely quantity per unit time or mass per unit time of fluid flowing through your surface. Right, so flux is interesting for a couple of different reasons. All kind of fluid related so far. We're going to find even more reasons to care about flux in time. Okay, so great formula, but it does make certain assumptions, and again, it assumes that the vector field is constant, and it assumes that the domain over which you're computing it is flat. And I'll remind you, again, that's the same assumptions that we were making over here. Constant vector field, flat / straight domain. Just that it was a curve, and over here it's a surface. Okay. So, how are we going to deal with that? Well, with over here in the curve context, we chopped it up into little pieces that are approximately straight and are also small, so the force is approximately constant, and chop it up, add it up. We're going to do the same thing over here. I'm going to take my surface now. I'm going to chop up my surface. Let's see here. Let's see if I can do this. I'm going to chop up my surface into little pieces of surface area like that are approximately flat and over which, because it's so small, the vector field, our integrand, is approximately constant. Same idea, right? Different context, different geometric details because now it's area instead of length. Okay, but morally equivalent. Okay. Now, there was the little sticky wicket of orientation. Let's talk about orientation now. Why did I need to know orientation in the curve context? Well, because I'm interested in work. And the amount of work it takes to hike up that trail is not the same as the amount of work that it takes to hike down that trail. They're very different experiences, right? So, all right, well, what does that have to do with flux? And, well, it's this, again, kind of morally the same. If you have a vector field moving through a piece of surface, you have to decide what you mean by what is the direction, the positive direction through that surface. And let's suppose you've decided that that's the positive direction that I have drawn up here. Then if that's the case, then fluid going like that would give you positive flux. But what about this? What if the fluid was doing this? This is a very different scenario, right? The flux, the quantity of fluid per unit time moving through that little piece of surface, it's fundamentally a different thing in that it's going the other way, right? So that is represented by the fact that these vectors, dot product with my orientation unit normal, is negative. Right, so we define as it is in this picture, we would say the flux is negative, and as it is in this picture, I don't know why I erased that. In this picture with this flow that way, flux is positive. Right, so what we're going to call the orientation unit normal. Let's see here. Let me put it back here. The orientation unit normal. You've got to pick on your surface which way through the surface is the one that you're considering the right, or the positive direction through the surface. And that choice is called the orientation unit normal, and that orientation unit normal paired with the surface makes this an oriented surface. So, new concept. Right? So, reminder, we've been talking about surfaces a lot. Never really thought of an orientation on a surface, particularly. But, again, think back to curves. We've been talking about curves for a long time, too, but we've quite a while ago had to come up with this idea, this new concept, this slightly more structured and sophisticated concept of an oriented curve to deal with that work situation. We need oriented surfaces to deal with this flux situation. Yeah.
So for the orientation of the curve, we're moving along the curve.
Correct.
And
Correct.
The surface, we're moving in and out of the surface.
Moving through the surface. That's right. That's right. No, that's right. And it's different physical motivations, different geometry. I mean, there's also the little matter of the curve is one-dimensional, the surface is two-dimensional, right? I mean, there's lots of geometric differences, absolutely. I'm not saying that everything's the same. I'm saying that of course, there are some things that are different, granted, right? But nevertheless, a lot of analogies remain. Yeah, it's a good point. Yeah. Everybody happy? Any other questions? Okay. All righty. Right. Okay. So, well, again, trying to keep the analogies, left side of the screen, right side of the screen. Here's our simple picture on each little piece of curve leading to this formula for dW, which helps us define a vector line integral. And, well, likewise, now looking on this little piece of surface, we can compute the flux through that piece of surface using this old formula, F dot N times surface area. Of course, our surface area here is ds. And that helps us define this thing called a vector surface integral. Totally analogous to how we define vector line integrals. It's flux instead of work. It's through instead of along. It's two-dimensional instead of one-dimensional. But the analogies are still extremely strong between these two computations. How do y'all feel about that? Is everybody on board with that? Now notice the notation, again, kind of naturally writes itself almost. We're adding up over a two-dimensional surface, so yeah, double integral. In fact, as you write this down, you might even still be, one could say, I was expecting this to turn into a scalar surface integral. So I used scalar surface integral notation. You could be forgiven for not realizing once you write this down that, oh my gosh, there's an orientation issue coming up. So very natural to use double integral notation. Again, this is just a recopy. And so vector surface integral. Now there is a notational thing here that I'm going to point out. This thing here, little n times ds, is pretty analogous to this thing over here, t ds scalar. Let's think about what t ds scalar is. T is a unit vector describing the orientation. Right? Well, let's look over here. What is little n? It's a unit vector describing the orientation. It's very analogous. Right? Let's come back over to here. What is the, let's see, what is the ds here? ds represents the size of a piece of curve. What is the ds here? It represents the size, now area instead of length, of course, but it's the size of a piece of surface. So what we have over here, this TDS thing, right, that was part of that notation for our integral, very naturally rewritten as a dx vector because, well, in a couple of different ways you can think about it, but the way I want to push on this right now is that TDS tells you the direction and the size of the piece of curve that you're interested in. Okay, well, what can I say about this product? Whoops, color choices. This piece, this thing here, NDS, it tells you the orientation and size of this little piece of surface. So this thing plays a role that is very analogous to this thing. And with that in mind, this, for the same reason that we rewrote that as dx, likewise, this thing here is very commonly rewritten as ds vector. That's just a notational choice. One could motivate different names for notations that would kind of make sense, and I'm open-minded to a lot of things, but the thing is, this is very standard. This is the notation I'm going to be using. This is the notation that the book uses, I'm fairly sure I recall, and so I think this just makes sense for that reason. Okay, is everybody comfortable? Okay. All right. So in the same way that this is my favorite notation for vector line integrals, right? I like the fact that you can see the vector aspect of it. It's just right there. It's also very compact. Everything you're looking at is geometrically natural, physically natural. Hard to beat that as a notation. Likewise, this is my own personal favorite notation for vector surface integrals. And there's other options. You could write it like that, I suppose, right? But it's a little clunkier. And again, I think everything in here makes sense. The F, that's the vector field. The DS is a single thing telling you everything you need to know about your piece of surface. So that makes sense too. Anyway, you will see different notations in my notes and my lectures. You're going to see this one most often. Okay. Alrighty. So, how do we compute these things? Let's see here. Yeah. Right. Yeah, I'll see the analogy starts to get a little different at this point. So let's see. Here we go. Okay, so how do we compute this integral? All right, so now most of what's on the screen here is just reminder. Remember, when you have a parameterization of a surface, then there's a parameter space, parameters S and T, let's say, and then of course that's parameterizing a surface in XYZ space, and we already know about the stretching factor. We've already worked all that out, right? So what do I do with all of this? if I have a flux that I want to compute, and the observation is this, that if I plug in for what the ds scalar is, and then if I look at this thing right here, and now before I get into talking about this, I want to acknowledge the asterisk out here, and I'm about to commit a math crime, and I just want the record to show I know I'm committing the crime as I'm doing it. I don't want to get distracted though in the issue at hand that I'm gonna violate here, because it's a whole other thing, and we'll get to that issue in a minute. So for the moment, I'm going to sweep this under the rug. Don't worry about it for the moment. If you want to try to imagine for yourself see if you can catch me. Right? Good. Go for it. If you think you know, please keep it to yourself. I'll reveal the crime in just a minute. But anyway, all of that said, I mean, it seems to make sense that if you look at this expression, I've got the unit vector pointing in the direction of capital N. This is the magnitude of capital N. This product then, I know the direction is the same, I know the magnitude is the same, feels like it's the same as capital N itself. Reasonable? Yeah, something to think about there. Let me say this is sufficiently close to right that I'm going to run with it for the moment, and then again there is a subtlety that I'm again deliberately committing a crime here, and we will talk about that subtlety in a minute. But this is close enough to right that this is worth running with for the moment. Okay. All right. So when you're doing an accumulation of flux over a surface, as is I think very nicely represented by this notation, right? In terms of just easy to write on the page, easy to relate to the question at hand, compact, fewest pen strokes, that kind of thing. Computationally, if you do want to plug and chug, pull back through a parameterization and take a deep breath and plow forward, there's your formula right there. Notice everything here is written in terms of the parameterization. Now let's do it. Let's actually compute one. Okay, vector field given. And let's see here. I want to compute it says here compute the flux through, let's see, okay, I've got a graph. Cool. I like graphs. They're easy to parameterize. Specifically the part of that's above the unit square. Okay, so let's think about how to parameterize this thing. How do I parameterize that? Well, okay, graph parameterization, of course. Right? Now, by the way, let me point out that we're seeing in action now a claim that I made a while ago. Why do we need to learn how to parameterize surfaces? Well, we need to learn how to parameterize surfaces because eventually we'll be defining integrals on surfaces, and we will be pulling back through parameterizations. And here we go. There, I needed that parameterization for the purpose of being able to pull back, aka compute with this formula. All right, so all that business about parameterizing surfaces, this is our first example of why we really need that. Right? A first example. Okay. All right. So we take the various partials. We take their cross product. And easy to crank that out, as it turns out. And let's see here. We plug and chug. Let's see. Our vector field is that, which is this, believe it or not. Okay, now wait a second. It doesn't look like that. How did the thing that was up there turn into this thing down here? Well, don't forget, our parameterization is telling us our formulas for X, Y, and color choices, Z. Yeah. And so up here, for example, this Z is that thing. Is everybody with me? It's easy to kind of oops that. Don't make the mistake of, losing track and, I don't know, thinking of, oh, well, that's in the first entry, so I guess that must be X or something like that. No. You got to be really careful with what is what, and don't forget that the parameterization tells you your parameters. And so, for example, this X right here, well, again, that's, oh, man, I could do better than that. This X right here is S. Everybody happy? Okay. All right. Okay, so F is all of this business. And then, again, I just got through computing my capital N. There's my capital N. Just a matter of plugging it in. DSDT, of course. Colors. DSDT remains DSDT. So we're in business. Wait a second. One other little detail here. What about above the unit square? How does that play in, this whole above the unit square thing? Well, above the unit square describes the unit square then in the XY plane. The unit square in the XY plane is telling you then the range of values of X and Y. And don't forget, X and Y are S and T because of our parameterization. So this unit square is not just telling us the range of values of X and Y, it's also telling us the range of values of S and T. Everybody follow that? That's an easy one to get tripped up on. All right. Okie dokie. Okay, and so integral, and so boom. This is a double integral at this point. Easy double integral, no less. Polynomial, constant bounds. This is a super easy calculation at this point. Yes?
Wouldn't the unit square be centered at the origin?
No, I get where you're coming from, but the convention of the term, the unit square, is that it is... Let's see here. So the unit square is this thing right here. Yeah, it's from 0 to 1 and 0 to 1.
So if we were to say unit circle, we'd say...
Units, the analogy is not good. The unit circle, I hear where you're coming from, right? The unit circle is that circle right there. Yeah.
Okay.
Yep, yeah, and I understand your discomfort. Yeah. Yeah, it's just terminology. Anybody else? Right. Okay. Let's ask the question. Which, by the way, we did when we were talking about vector line integrals, right? We asked the question: does the parameterization matter? And the answer was, well, it depends on whether or not the parameterization follows the orientation. It mostly doesn't matter, but it does matter that you parameterize the same direction that you're actually going. So we're going to ask now the analogous question here. Does the choice of parameterization matter? And, well, again, kinda. And the main issue is, just like it was for vector line integrals, are you parameterizing the correct direction? But let me show you how that looks. It looks different in this surface context. So, quick reminder, here's our parameter space. Here's our parameterization. That builds our surface, right? And of course, with the surface, you can talk about the various partials and the capital N vector and the ds scalar, blah, 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 right? All this stuff that we've already built up. So most of what's on the screen here, again, old news. So here's the concern. When the question asks you about a surface and it says, I want to compute the flux either, upward through the surface or downward through the surface, whatever, right? The question really should, and in some sense has to, include an indication of, well, which way is the positive direction through the surface? There's no rule that says up means positive, right? It's just not. you can be interested in stuff going downward through a surface. That's how basketball works. After all, ball's got to go downward through the hoop, right? So there needs to be an indication, and that indication is done by the orientation unit normal, and that's a vector. We talked about this a few minutes ago. It's one or the other of these, indicating which direction through the surface is the correct, the positive, the one I'm interested in, right? Direction through the surface. Okay, now, here's the thing. When you parameterize the surface, most of the time that you parameterize a surface, you're not thinking about orientation. It's hard to even, at a glance, it's hard to even have any sense for how a parameterization has an orientation. But it does, because the X parameterization gives you all of these velocity vectors, which gives you your capital N vector, the normalization of which is your parameterized unit normal. And this is the one that I was making, I was complaining about Colley's use of the term standard, because again, it's not standard to the surface. It's a peculiarity of the parameterization itself. Right? So when you create a parameterization, you're arbitrarily picking an orientation, not even realizing it. Right? Nobody's thinking about, well, very few people are thinking about what that's going to end up being as they parameterize. Right? And thus, it's a coin flip. When you parameterize a surface, it's a 50-50 chance that you parameterized the right way, and it's 50-50 you parameterized the wrong way. Right? So, for example, if the question was given as, we want to compute the flux downward through this surface, described by whatever means I described the surface, and so I specifically ask for flux downward through the surface. If I were to have parameterized with that, and thus ending up with this capital N vector, and thus this upward parameterized unit normal, I parameterized it the wrong way. Does everybody see the problem? And again, this is a really nasty little problem intuitively, because if you're thinking about parameterizing curves, it's really much more clear when you're talking about a curve parameterization. You can almost see, just depending on what you're parameterizing, I suppose. But sometimes it's just very clear when you're parameterizing which direction you're moving as you parameterize, because our parameter is time, and time's something we have intuition for, and it's just usually pretty clear. With surfaces, it just isn't. So that's the problem. That's our concern. Is everybody on board with that? So this was the math crime I committed a little ways back. When you may recall, I pointed out this asterisk, and I confessed, there's an issue here that I'm failing to address. Well, the problem was that the normal vector that I had at that stage of the calculation, that was the orientation unit normal. That was the orientation that came in the statement of the question. And when I said, hey, check it out, look at what I've got in yellow, that's the same as the capital N vector. Well, the capital N vector, its direction is the parameterized unit normal. I was therefore assuming inappropriately that these were the same. And again, 50% of the time, they're not. So, mea culpa. Does that make sense to everybody? Okay. All right. So, how do we deal with this? Really good news. You don't have to worry about it as you're parameterizing. Just parameterize any way you want. Don't even worry about it as you parameterize. At some point in the calculation, it will present an opportunity to visually inspect and see if you parameterize the right way. And if you accidentally parameterized upside down, just, write, oops, smiley face, parameterized it the wrong way, haha, -1, draw an arrow, boom. That's all you got to do, right? For God's sakes, don't reparameterize. There's no need, right? If you parameterized it upside down, you're just off by a factor of -1. You and everybody else know it. So you fix it by just multiplying by -1. Yes?
So how do we know it's upside down from the picture?
Well, because there's only two options. Oh, you're saying how do we know in which case?
Right.
Yeah. I haven't gotten to that yet, and it looks like I won't be getting to that today. It's going to be in the this example that's coming up. So we are out for today, drawing the line right there, and I'll answer your question on Wednesday. Yeah. All right. See y'all later. Have a good one. Don't forget to come get me to do your attendance.